Hello, in this lecture we will find out the area of a circle. In the drawing we have a semicircle. Inside this semicircle we have a circle, and our mission is to find out the area of this circle. In addition, we know that line segment AQ equals to 2 units in its length, line segment TB equals to 8 units in its length. This is angle AQT, that is a right angle. This is angle STB, that is also a right angle. Again, our mission is to find out the area of this circle that is inside the semicircle. So, first of all, we'll define the relevant points to this question with letters. We define the center of this semicircle, this point, as point H. We define the center of this circle, this point, as point M. We define the point of tendency of tangent. We define the point of tendency of tangent AB with this circle, this point, as point Y. And we will define the touching point of the big quarter circle with this small circle. This point is point Z. We know that AB is a straight line, so if we focus on the upper side of the straight line AB at point Q, here the sum of the areas must be equal to 180 degrees, according to rule 3, that the sum of the areas on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of AB at point Q? We have this angle that is equal to 90 degrees in size, plus this missing angle. In total they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, we focus on the upper side of the straight line AB at point T. Here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of AB at point T? We have this angle that is 90 degrees plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle, the angle ATS, must be equal to 90 degrees in its size. Here we define the point of tendency of tangent ST with this circle as point L. And finally, we define the point of tendency of tangent PQ with this small circle as point K. We join points M and Y together by a straight line. So what is the definition of line segment MY? Line segment MY starts from point M, that is the center of this small circle, and ends at point Y, that is a point on the small circle itself. So this is exactly the definition of a radius. Therefore, MY is the radius of this circle. We define the radius of the circle as x. Therefore, MY equals to x according to our definition. It is the radius of the circle. And we have here, we can implement rule 1. Rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So we have a circle and we have the radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule all 1. So we can actually implement all 1 in our drawing. Then in our drawing we have the radius MY that is drawn to point Y, that is the point of tendency of tangent AB with this small circle. Whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius YM. If AB is perpendicular to YM, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to all 1. Likewise, we join points M and L together by a straight line. ML is the radius of this circle that is equal to x. Here the radius ML is drawn to point M, that is the point of tendency of tangent ST with this small circle, and whenever your radius is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LM. If ST is perpendicular to LM, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to 1, 1. So actually, we can do for the other ML TY. So for the other ML TY, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral MLYT we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be its left angle plus a square. So we relate to this quadrilateral MLYT as a left angle, but we know that the opposite sides of left angle are equal to each other. So left angle MLTY side ML must be equal to the opposite side YT. But ML is x, therefore YT must be also equal to x. Likewise, in the same left angle MLTY side MY must be equal to the opposite side LT. But MY is x, therefore LT must be also equal to x. So we found out that the quadrilateral MLYT is not a rectangle but a square because all of its sides are equal to each other. Each side is equal to x. So write it down. We found out that quadrilateral MLYT is a square. Likewise, we join points M and K together by a straight line. MK is of course the radius of this circle that is equal to x according to our definition. Again, the radius MK is drawn to point K, that is the point of tendency of tangent PQ with this circle. Whenever your radius is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius KM. If PQ is perpendicular to KM, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule all 1. So inside quadrilateral MKQY we have 1, 2, 3 right angles. Again, the sum of 3 right angles is 270 degrees. 270 degrees plus the size of this 4 facing angle, total must be equal to 360 degrees. Therefore, this missing 4 angle must be equal to 90 degrees in its size. So inside quadrilateral MKQY we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be this left angle plus a square. So we relate to this quadrilateral KMQY is rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle KMYQ, side KM must be equal to the opposite side QY. But KM is X, therefore QY must be also equal to X. Likewise, in the same rectangle KMYQ, side MY must be equal to the opposite side KQ. But MY is X, therefore KQ must be also equal to X. So we should know that quadrilateral KMYQ is also a square. Angle KML, this is angle KML. Angle KML equals to 90 degrees plus 90 degrees, that is 180 degrees. We know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore KML is a straight line. Here KML is a straight line. But KML is a straight line that touches the circle at 2 points, K and L. Therefore KML is a chord. Again, KML is a chord. But KML is a chord that passes through point M, that is the center of the circle. And we know that any chord that passes through the center of the circle is defined as diameter. So KML is the diameter, therefore KL is also the diameter of the circle. So I write it down. KL is the diameter of the circle because it passes from point M, that is the center of the circle. So KL is the diameter of the small circle. Okay. Anyway, KL is a diameter, it is absolutely a straight line, so therefore shape KLTQ, this shape is a quadrilateral. Why? Because we have here 4 sides. 1, 2, 3, and this is the 4th side. Because KL is one straight line. So we have a quadrilateral KLQT. Inside quadrilateral KLQT we have 4 right angles. And therefore quadrilateral KLQT is a rectangle. Okay, quadrilateral KLQT is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle KLQT, side KL must be equal to the opposite side QT. But KL is the diameter of the circle that is equal to 2x. Therefore QT must be also equal to 2x. Also the diameter of the circle is equal to 2x in its length. So I'll write it down. I shall find out that line segment QT is also the diameter of the circle, and it is equals to 2x units in its length. Okay, so QT equals to 2x. QT equals to 2x. So what is the radius of the semicircle? AB is the diameter of the semicircle, therefore the diameter over 2 is the radius of the semicircle. So AB over 2 is the diameter of the semicircle. So what is the value of AB over 2? AB in total equals to 2 plus 8 plus x plus x. So in total AB equals to 2 plus 8 is 10 plus 2x. So AB is 2x plus 10. and AB over 2 is the radius. So the radius AB over 2 is 2x plus 10 over 2. 2x plus 10 over 2 is 2x over 2 is x, and 10 over 2 is 5. So we will define the radius of the big semicircle SR or capital R. So the capital R, that is the radius of the big semicircle, equals to x plus 5 units in its length. Okay. Here we can implement rule 9. Why? Because we have an internal notch between the big semicircle and this small circle. That is to say, they are touching each other internally at point Z. Again, they are touching each other internally at point Z. And whenever you have an internal notch between two circles, you can implement rule 9. I'll repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. We have here two circles, they touch each other internally at this point, point P. The center of the big circle is at point O. The center of this small circle is at point M. And the straight line that connects their centers together is the straight line OM. And according to this rule 9, the straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass through point P, or OMP is one straight line. Again, OMP is one straight line. We can actually implement rule 9 in our drawing. Why? Because in our drawing, as I already mentioned before, the semicircle touches this small circle at point Z. So they have an internal notch between them at point Z. And so according to, therefore we can implement the rule 9. And according to rule 9, the straight line that connects their centers together must pass through their touching point, that is point Z. So the straight line of the big semicircle is at point H. The straight line of the small circle is at point M. And the straight line that connects their centers together is of course the straight line edge M. The straight line edge M must pass through point Z, that is their touching point. Or edge MZ is one straight line. Again, according to rule 9, edge MZ is one straight line. And again here, edge MZ is one straight line. So I connect the points edge and M together by straight line. According to rule 9, the straight line edge M must pass from point Z, that is their touching point. Actually, this is their touching point. You can see here the straight line edge M. This is the straight line edge M passes through their touching point, that is point Z. Okay, but what is the definition of line segment MZ? Line segment MZ starts from point M, that is at the center of the circle, and then at point Z, that is the point on the circle itself. Therefore, ZM is the radius of the small circle that we defined as X. And the radius of the semicircle is defined as capital R. So, what is the definition of line segment edge Z? Line segment edge Z starts from here point H, that is the center of the semicircle, and that's at point Z, that is a point on the semicircle itself. Therefore, this is exactly the definition of a radius. So edge S is the radius of the semicircle, that's equal to x plus 5. And Zm is the radius of the small circle, that's equal to x. So what is the length of line segment MH? Repeat again, what is the length of line segment MH? MH equals to MZ minus MH equals to HZ minus MZ. Again, HM equals to HZ minus MZ. So I write it down. MZ equals to, actually the missing side MH equals to HZ minus ZM. So the missing side MH equals to HZ, that is the radius of the semicircle, is equal to x plus 5 minus Zm. Zm equals to x, it is the radius of the small circle. So in total, mh, the missing side mh, equals to x plus 5 minus x. So x minus x is 0, so mh equals to 5. So we found out that mh equals to 5 units in its length. This is line segment mh, that's equal to 5 units in its length. In the next step, we'll find out the length of line segment YH. The length of line segment YH. So this line segment YH. YH equals to AT equals to Y. The length of line segment YH is actually equals to AH, that is actually the radius of the semicircle, minus AQ minus QY. Again, AH, that is the radius of the semicircle, minus AQ minus QY equals to YH. So I write it down. Actually found out that YH equals to AH minus AQ minus QY. So YH equals to AH. AH is the radius of the semicircle, is equal to x plus 5 minus AQ. AQ equals to 2 units according to what is given us the question, minus QY. QY equals to x. So YH in total equals to x plus 5 minus 2 minus x. X minus x is 0 and 5 minus 2 is 3. In total, we found out that YH equals to 3 units in its length. This is line segment YH, that is equals to 3 units in its length. So in the next step, I'll copy the right green triangle MYH in a new page, and we will implement the Pythagoras theorem on this right green triangle MYH. Here by PT is the equation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side MY equals to x, it is the radius of the circle. We just right now found out that YH, side YH, equals to 3 units in its length. And we already found out that the hypotenuse M edge equals to 5 units in its length. So actually, this is the right grand triangle MY edge that I quote from the original drawing. According to the Pythagoras theorem, in this right triangle MY edge, MH square equals to MY square plus YH square. So I write it down. MH square, that is the square of the hypotenuse, must be equal to MY square plus YH square. MH is 5, therefore MH square is 5 squared, that is 25. And it is equal to My square. My is y, My is x, therefore My square is x squared plus YH square. YH is 3, therefore Y square is 3 squared, that is 9. So if we found out that 25 equals to x squared plus 9, we subtract 9 from this equation and finally we get that x squared equals to 25 times 9 is 16. X squared equals to 16, we take out of this equation and get that the radius x of the circle equals to 4 units in its length. Our mission is to find out the area of the circle. The area of the circle equals to pi r square, r is the radius. And according to our definition, the radius r equals to x, therefore it is pi x squared. And we already found out that x squared equals to 16, so it is pi times 16. So if we found out that the radius of this circle equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. And that is the answer to the question. So in the next step, I'll summarize the lecture. So in this lecture, we found out the radius of this small circle. Actually, in the drawing, we have a semicircle, a big semicircle. Inside this big semicircle, we have this small circle. And in addition, we know that 9 segment AQ equals to 2 units in its length, 9 segment edge TB equals to 8 units in its length. This is angle PQA, that is the right angle. This is angle STB, this is also a right angle. Repeat again, our mission is to find out the area of this small circle that is inside the semicircle. So first of all, note that AB is the diameter of the semicircle, therefore it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point Q, the sum of the areas must be equal to 180 degrees, according to rule 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of AB at point Q? We have this angle, that is the right angle, plus the missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, we'll continue to focus on the upper side of the straight line AB at point T. Here, the sum of the angles must be equal to 180 degrees according to the same rule 3. So which angles we have at the upper side of AB at point T? We have this angle, that is right angle, plus this missing angle. In total, they must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. Then, we define the relevant points to this question with letters. We defined the center of this circle, this point is point M. We define the center of this semicircle, this point is point H. We define the point of tendency of tangent AB with this small circle, this point is point Y. We define the point of tendency of tangent PQ with this small circle, this point is point K. We define the point of tendency of tangent ST with this small circle, this point is point L. And finally, we define the touching point of the big semicircle with this small circle. This point is point Z. Then the next step actually connected points M and Y together by straight line. Point M is the center of this small circle. Point Y is the point on the circle itself. Therefore, MY is the radius of this small circle. We define the radius of this small circle as x. Therefore, my equals to x. This is the radius of this small circle. Here, implemented rule 1, we have the radius my, that is 1 to point y, that is the point of tendency of tangent AB with this small circle. Whenever we have a radius that is 1 to the point of tendency, then tangent AB will be perpendicular to the radius ym. If AB is perpendicular to ym, it means that this angle equals 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points M and M together by straight line. ML is the radius of this small circle, that is equal to x. Again, the radius ML is 1 to point M, that is the point of tendency of tangent ST with this small circle. Whenever a radius that is 1 to the point of tendency, then tangent ST will be perpendicular to the radius LM. If ST is perpendicular to LM, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule 1. Fine. Now, we created a quadrilateral ML TY. Inside quadrilateral ML TY, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 free cylinder, in total they must be equal to 360 degrees. Therefore, this 4 free cylinder must be equal to 90 degrees in its size. So inside quadrilateral MLTY, we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be at this right angle, if not a square. So we relate to this one quadrilateral MLTY as a right angle because it has 4 right angles. But we also know that the opposite sides of left angle are equal to each other. So in left angle MLTY, side ML must be equal to the opposite side YT. But ML is x, therefore YT must be also equal to x. Likewise, in the same rectangle, according to the same rule, side my must be equal to the opposite side LT, but my is x, therefore LT must be also equal to x. We should find out that quadrilateral MLYT is not a rectangle but a square because all of its sides are equal to each other, each side equals to x. Likewise, we have here quadrilateral KMYT. Inside quadrilateral KMYT, we have 1, 2, 3 right angles. This angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1, because we have the radius MK, that is 1 to point K, that is the point of tendency of tangent PQ with this small circle. Whenever a radius that is 1 to the point of tendency, then tangent PQ will be perpendicular to the radius KM. If PQ is perpendicular to KM, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside quadrilateral KMYQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 free cylinder, in total they must be equal to 360 degrees. And therefore this 4 free cylinder angle must be equal to 90 degrees in size, and I'll not repeat all the same process. This quadrilateral is a rectangle because it must be at least a rectangle if not a square because it has 4 right angles. But we know that the opposite sides of rectangle are equal to each other, so rectangle KMYQ, side KM must be equal to the opposite side QY. But KM is x, therefore QY must be also equal to x. Likewise, according to the same rule, rectangle KMYQ, side MY must be equal to the opposite side KQ. But MY is x, therefore KQ must be also equal to x. Again, we shall find out that quadrilateral KMYQ is not a rectangle but a square because all of its sides are equal to each other, each side equals to x. Okay. Here we shall find out that KL, we have here KML, or line segment KML, or we have angle KML is equals to 90 degrees plus 90 degrees, that's 180 degrees. So this angle equals to angle KML equals to 180 degrees inside, and we know that any angle that is equal to 180 degrees inside, it is defined as a straight line. So KML is a straight line, therefore KL is also a straight line. Again, KL is also a straight line, and therefore shape KLTQ, this shape is a quadrilateral because it has 4 sides, 1, 2, 3, 4. Inside this quadrilateral we have 1, 2, 3, 4 right angles, and therefore any quadrilateral that has 4 right angles must be this right angle is not a square, so we relate to this quadrilateral as a rectangle. But we also know that the opposite sides of rectangle are equal to each other, so in rectangle KMTQ, side KL must be equal to the opposite side QT. But KL equals to x plus x, this is 2x, this is the diameter of the circle, therefore QT must be also equal to 2x. Okay? So here we can implement rule 9 because we have this small circle touches the big semicircle, the attaching point is at point Z. And whenever you have an internal notch between two circles, that is to say whenever two circles touch each other internally, like here, you can implement rule 9. So I'll quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together must pass through their touching point. We have here two circles. Those two circles touch each other internally here at point P. The center of the big circle is here at point O, the center of this small circle is here at point M, and the straight line that connects their centers together is of course the straight line OM. This straight line OM must pass through their touching point at this point P, or OMP is one straight line. Again, OMP is one straight line. We can actually implement all 9 in our drawing. We have internal notch between the small circle and the big semicircle. They touch each other internally at point Z. The center of this small circle is here at point M. The center of the big semicircle is here at point H. And the straight line that connects their centers together is of course the straight line HM. This straight line HM, according to rule 9, must pass through point Z, that is their touching point. Or HMZ is one straight line. Again, HMZ is one straight line. If HMZ is one straight line, it means that HZ is a straight line. But what is the definition of the straight line HZ? It starts from the center of the semicircle, that is to say from point H, and ends at point Z, that is the point on the semicircle itself. So this is exactly the definition of a radius. Therefore, HZ is the radius of the quarter circle. But what is the radius of the quarter circle? We note the diameter of the, what is the radius of the semicircle? HZ is the radius of the semicircle. What is the radius of the semicircle? The radius of the semicircle is AB. The diameter of the semicircle is AB, therefore the radius equals to AB over 2. So AB equals to, in total, 2 plus 8 plus 2x. 2 plus 8 is 10. So in total, AB equals to 2x plus 10, and AB over 2 is the radius. So 2 plus x plus 10 over 2 is the radius of the semicircle. 2 plus x over 2 is x, and 10 over 2 is 5. So in total, the radius of this semicircle, capital R, equals to x plus 5. The radius of the small circle is x, and therefore the missing side M edge equals to MZ. Again, M edge equals to Z edge minus MZ. Again, Z edge minus MZ equals to the missing side M edge. Repeat again here. M edge equals to edge Z minus MZ. Edge Z is the radius of the semicircle that is equal to x plus 5 minus mz. Mz is the radius of the small circle, that is x. So in total, the limit inside mh equals to x plus 5 minus x. X plus 5 minus x is 5, because x minus x is 0. So we found out that the limit inside mh equals to 5 units in its length. Okay? So here we know that the radius of the green right triangle MYH, the hypotenuse MH is 5, and one side of the green right triangle MYH is x, it is the radius of the small circle. So what is the length of YH? From the drawing it is very easy to see that YH in total equals to AH, that is the radius of the semicircle. AH minus AQ minus QY equals to YH. Again, AH minus AQ minus QY equals to YH. Okay, here YH equals to AH minus AQ minus QY. AH is the radius of the semicircle, that is x plus y, minus AQ. AQ is 2, minus QY. QY equals to x. So in total, the missing side YH equals to x plus 5 minus x. X minus x is 0, and 5 minus 2 is 3. So if we found out that the missing side YH equals to 3 units in its length. In the next step, I copied the white green triangle MYH in a new page, and we implemented the Pythagoras theorem on the white green right triangle MYH in order to find out the missing side MY, that is actually the radius of the semicircle, that is the radius that we are looking for. And after we find the radius, to find out the area of this circle, it will be very easy, because the area will be equal to pi r squared. Okay. So actually, this is the right green triangle MYH that I copied from the original drawing. The hypotenuse MH is 5. The missing side, we already found out that side YH equals to 3, and side MY equals to x. It is the radius of the circle. According to the Pythagoras theorem, MH squared equals to MY squared plus YH squared. MH is 5, therefore MH squared is 5 squared, that is 25, and it is equals to MY squared. MY is x, therefore MY squared is x squared, plus YH squared. YH is 3, therefore YH squared is 3 squared, that is 9. So in conclusion, we found out that 25 equals to x squared plus 9. Here we subtracted 9 from this equation, and we found out that x squared equals to 25 minus 9 is 16. So x squared equals to 16, we took out of this equation, and we found out that x equals to the square root of 16, that is 4. So the radius of this small circle is 4, and therefore the area equals to pi times the radius squared. Okay, so the radius squared is x squared, that is 16. So pi r squared is actually pi x squared, because x is the radius, that is r. So the area of the green shape equals to pi x squared, and x is 4, therefore x squared is 16, so it is pi times 16. So the area of this small circle equals to either 16 pi square units, or in terms of numbers, it is equals to 50.265 square units. Okay, thank you very much.